Now, I realized yesterday that since I'm talking last, most of the things are going to have been said already. And of course, you've been in this track all day, right? No? Anyway, so here's a high-level slide. According to the FCC, if you look at downtime in or service interruptions in the telecoms industry, almost half is due to overload. So this definitely is a very critical problem. I wrote jobs a number of years ago. I actually presented it at the Erlang Workshop in Baltimore. Then I didn't use it myself for quite some time. We're actually using it now in Foyer Labs. And it's on GitHub. So there's the URL. And in that repository, you can also find the Erlang Workshop paper. So I'm not going to rehash what's in the paper or what I talked about in previous presentations. But basically, you could say that the principle with jobs is that you want to do gatekeeping at the borders of your system. So if you have incoming requests, this is really, before you commit capacity to handling that request, you want to make sure that you can actually see it through. And once you have committed to it, the best thing is if you can just service that request as efficiently as possible. That means that you will have core systems in here that preferably should just go at max capacity and not do a bunch of overload regulation. A parallel could be, for example, in TCP/IP networks, when they were trying to implement quality of service on TCP/IP, which was stupid because we could all have used ATM and we would have been happy. There were two competing approaches. One was actually to use the same strategy as an ATM, which was every node in the network had tons of buffers and 16 service classes, whatever, and could guarantee the quality of service contract. This becomes really expensive. And also, when you try to do this on TCP/IP, you would drive the sysops crazy. They hated it. So that was the IntServ model, and I don't think many people use that. It was beaten hands down by the DiffServ model, which it basically means you regulate at the edge nodes, and then in the core network, you go as fast as possible. Basically over-provision the core network, and you can do switching, for example, and just, once you've set up a path, just go as fast as possible through the network. And make sure that you regulate as far out, as near the customer as possible. And so jobs basically depends on the same type of strategy. Now, of course, if you see this as a whole Erlang system, then maybe these are actually different nodes, different Erlang nodes. And then you could run into the problem that over here, the system looks fine, but here it's actually getting overheated. So then you may actually need to do regulation between nodes as well. What you would want to do then is to have a higher priority on the work that has already been committed by some other node in the system. So the API for jobs is, well, one is you name a type of job. Essentially, as soon as you've gotten a request, for example, from the network, you decode it, you identify the work, and then you ask the load regulator whether you can press on. And it will either answer OK or maybe error if there is not enough capacity to run the job. There is a little wrapper here where you put your work inside a fun and you run that. Now this thing, depending on what load regulation you're running, it may actually give you some resources that need to be freed. If your process continues and runs other work, then it has to tell the load regulator that it completed that job. And then you have to call the function done. But if your process dies, which would be a typical Erlang way of doing it, you spawn a process, it asks for permission, it performs the work, and then it dies. Then you don't have to worry. The resources will be freed automatically. And then there are a bunch of other functions too, but they're basically administrative functions. So just to show you some live code, I took this slightly simplified from our system, where we're actually getting a JSON RPC request, and we have a queue that tells us that this is an RPC from the web, and then we run this function. We call the YAWS RPC handler session. And this gives us load regulation. And then it's a matter of configuration what parameters we set on this queue. But so you identify the entry points in your code where you're actually committing to doing some work, and then you just name a queue and you're done. Last year at EUC, Dizzy presented via video, because he couldn't actually come, a little experiment where he had integrated jobs into Riak. And then in his code, I actually copied this from his presentation. He uses the ask function, and then if he gets a go-ahead, he does stuff, Riak-y stuff, and then after that he calls done. Or if he gets an error, the work is rejected, then that's an error, obviously. He ran some basho bench tests. This was a throughput graph. This is where the system is not overloaded, and they're running about 70 operations per second with few errors. And here is an overload situation where you are running pretty much, well, a similar throughput. This is over 5 minutes, and obviously many more errors. So a lot of jobs are rejected, but you're still getting pretty high throughput. Now, in the opening talk, Mahesh mentioned that something has to give when you have an overload situation. So in these tests, these are latency graphs, and here we can see in the happy case, this is the 95th percentile. You have like 45 milliseconds. And here in the overload case, the mean is approaching that level. This is the median at slightly over 50, and here we're over 60 milliseconds. So you get longer delays when the work is being queued and we're rejecting jobs. So there is a cost to load regulation, but the benefit is you get fairly predictable performance and the system stays up, which is nice. So I thought previously when I've talked about jobs, I've talked about sort of the principles mainly, what it was designed for. This time I thought I'd give you some examples and give you a little bit more concrete information about how to use it. So the one way to create a queue is to have a rate-limited queue. You can specify whether it's FIFO or LIFO. FIFO is the most common. It's also the default. And what jobs will do is that it will timestamp every request when it comes in. and then it will put them in a queue, an ETS-based queue, and then it will calculate a frequency for how fast to pull jobs out of the queue. So essentially, it tries to, if you've set it to, say, 100 requests per second, it's going to try to pull 100 requests per second out of the queue with some decent time slice. And you can specify things like maximum length of the queue, maximum time. For example, in the telecoms world, where I used to be, then when there is a request to set up a phone call, the protocols actually have a lot of timers in them. So if the request has been in the queue for a while, you don't have to service it because the caller has given up already, because all kinds of timers in the protocol have released. Now you can also do counter-based limiting. Then you basically say how many jobs you want to allow at the same time. So it's pretty much a token bucket. You keep taking tokens out of the bucket, and this is where you need the done function. You need to actually return those tokens. And you can actually then also have these buckets being global, so you can have multiple queues pulling out of the same token bucket if you want to do that. So having a rate-limited queue, this would be an example. I decided I was not going to, first I thought I'd just do live demos, but the main difference is you see these things popping up with intervals. Actually, here I would actually be just repeating the same command. I've started jobs. That would be command number 1, application start jobs. And here I add a queue. I call it queue. And I say that this is a standard rate queue. That means that this is how many requests per second I want to allow. And it uses some other default parameters. And then I use this run function. And the function I execute is just writing job and the time. And if I repeat it, it will actually wait if I do it fast enough so that I can do at most 1 per second. Now, you can actually also put a little stateful logic into the queue dispatch. So here, I add a queue, also a standard rate 1 second, but I provide a fun with some clauses here. It initializes to 0 and 5, basically saying, here we go. I'm going to return the first digit, and then I'm going to increment modulo size, so modulo 5 here. So this is going to be called every time there is a dispatch, and it's going to return a new value and a new state. And I'll get back to this later. Now, of course, this runs in the load regulation server, so it had better be correct and it had better be fast, because otherwise it's going to interfere with stuff. But here then, the client function, now I can call it a function of passive function of arity 1, and then jobs will give me this opaque state that it passes to the client, and I can pull the job info from the opaque state, which is undefined if there wasn't a state fun in the dispatcher. But here I will get that number back. So it goes from 0, 1, 2, 3, 4, and then starts over at 0. So if I want to have a front-end queue that goes round robin across a number of nodes or whatever, then I could do it this way. So each job would get whatever, a new state, if you want to do it that way. So that could be a simple way to load balance over multiple workers. Now, I can also send in a call to that state fun, let's go back to, that's this one, call, and I set a new size, and then I just start over from 0 and do modulo 3 instead. So then I've actually changed my state in the dispatch function. So that's then stateful rate limited dispatch. Now, since I have rate regulation, I figured that if you do away with a queue and you just give the load regulator a fun, then you have a load generator. So, if you create a producer and you provide a function, then you can actually generate work at a given frequency. So here I've created a queue called P, and it's a producer, and it will, at once every second, it will just print this out. So then it will start printing out every second here. So, and since you can update these regulators at runtime, I don't have an example for that, you could actually then have a producer that where you keep tweaking the rate so that you can go up and down. You can also create a passive queue. Then you have to use the functions enqueue and dequeue. And here I have a little function that I'm going to use in a producer. There. And that function will just print that it's starting, and then it will do a dequeue. And if the queue is empty, it will actually hang here until there is something to pull out of the queue. If there is something in the queue, it will just take that and run with it. And then it prints the result, and then it dies. The producer will spawn a process for every job. So it will spawn a process that prints out its PID and then waits for something to enter the queue. So what happens here is that once I add this producer queue, which uses a counter-based regulation saying I want to allow 3 workers, immediately it's going to start 3 PIDs, and they're just going to wait there because there's nothing in the queue. I put something in, and immediately one of the workers is going to pull that out. And actually it gets the timestamp where it was enqueued and the entry, which is just the atom, job 1. And then it's done, and another PID is starting. So this then becomes sort of a worker pool that just pulls work out of this queue as long as there is work to be done. Okay. There are also some queue inspection functions. You can call queue info, and this was actually a rate-based queue, so it will tell you what this is actually the queuing module. You can plug in your own queuing module if you want to, which, for example, Jesper could do with his queuing logic. I'm not using group here, but you can group queues into that use, for example, the same, a higher level regulation. I'm saying out of these 5 queues, I will have a maximum of 1,000 requests per second, but then you can have different rates per queue and things like that. This is a rate limiter or rate regulator where I have the limit and modifiers. I will get into those. The modifiers can act on feedback from load samplers. And then max time, max size are undefined. And then you can also get things like latest dispatch, how many jobs have been approved, how many jobs are queued, things like that. Now, In a distributed overload case, one example is Mnesia. I don't know, how many of you have used Mnesia in a distributed setting? Many. How many have suffered weird overload situations? Okay, many of you. Yeah, so one particularly nasty case is, say you're running lots of dirty writes or whatever on one node. They're pretty cheap, right? But they're replicated to another node. And then the Mnesia transaction manager on that side it actually does more work than the originating node. So it tends to fall behind. So what it does is it has a couple of safeties. It will sample the message queue length of the Mnesia TM process. And if it exceeds a certain limit, it will generate an event saying that it's overloaded. It also detects whether a transaction log dump is triggered while the previous transaction log dump is still being processed. And then you get those Mnesia overloaded events. The problem is that event is issued here. But this is where the overload came from. So it doesn't actually generate that event on every Mnesia node, only on the node where it's detected. And this does us no good unless we have installed an event handler on every node that talks to the other nodes and sends feedback to them so that they can slow down. Otherwise, this node is just going to die eventually. So what jobs does, if you're running in a cluster, is that all the jobs instances will broadcast overload information to each other. And there are a couple of predefined load samplers in jobs, but you can write your own. I'm going to show you how it's done. It's not terribly difficult. And so if an overload is detected on one node, it's going to send that to all jobs instances. And this is where the modifiers come in. The modifiers actually tell you or instruct jobs with how much you want to reduce the rate of certain queues. So then you can add factors there. I will show you the Mnesia overload sampler. So it subscribes to system events when it started. And then there is this abstraction where you can provide sort of a list. I call it levels, which is actually used down here with the function jobs sampler calculate. So this is where you're going to calculate the amount of overload. And in the case of Mnesia, what's really interesting is how long has the overload been going on. So here, for example, I provide in this list, this is sort of a multiplier. If in the beginning I have a multiplier of 1, say after, this is just my wild guess. I haven't sort of empirically tuned these numbers, but so they're in there. After 30 seconds, I increase the multiplier to 2. After 45, I increase it to 3. And then after a minute, I increase it to 4. So I keep reducing the load if the overload situation doesn't eventually go away. So then the system should become reasonably self-tuning. It will eventually, hopefully, throttle enough that Mnesia can catch up. So this is your callback module. You have the init function, and then you have handle message. So this is Mnesia's event, where it says this is a dump log overload. Here is the message queue length overload. And what I do is I just log that now I have overload. there are a couple of things you can do. This is a simple thing where I'm saying either ignore if I get something else that I don't recognize, or if I get these, then I have overload. And then this function, sample, I check whether I ask Amnesia if it's overloaded. And that will actually possibly reset this, this flag. So basically this jobs will then, using this, determine some kind of overload factor that it will pass on to queues that then use, for example, the amnesia modifier match on this particular type of overload. And then it will provide a number that is then multiplied by that and used as a percentage to reduce the load. Was that reasonably clear? So with, for example, CPU sampling, you can use CPU sub. For some reason, when you call it the first time, you just throw away the result, but that's per the documentation. But you call CPU sub util, and then you figure out what amounts to overload, and that's not entirely trivial in a multi-core system. But anyway, this is for you to tweak if you want to. The thing is here, say if it's a single CPU system, then really this is level-based. If it's 100% CPU, then I want to throttle more than if it's 80%. Maybe I don't see it as overload. But if I'm approaching 100%, then I'm going to start upping the factor, the throttle factor. So this is then just level-based. The previous one was time-based. But you can, for example, in this calculate function, you don't have to use this utility function. This was just sort of my attempt at making something that's reasonably user-friendly. But otherwise, you can use a random generator if you want to. So, holy cow, I thought this was going to take a long time. So what I'm planning to do, there is some obviously continuous code cleanup. One thing that is a bit annoying right now is that if you give jobs the wrong parameters, it may appear to accept it. And but then it's not going to do, it doesn't do enough checking on what you put in when you define the queues. But on the other hand, if you read the non-existent documentation carefully, then you don't have to make any mistakes. So I'm also going to write some more documentation and examples. The presentation here gives you some examples. And one of the ideas here is that one thing I've tried to do with jobs is to make it really easy to get started. So essentially, if you want to create a rate-limited queue or a counter-based queue, that, as I hopefully showed, is not terribly difficult to do. And then you can put in the load regulation requests, and then you're basically up and running, and you have load regulation, and then you can start tuning it once you get into load tests and figure out what the parameters should be on each queue. And then if you want to do adaptive load regulation, then that's probably fairly far along in your project. So essentially the idea is when you grow into really wanting to tune this, then jobs will provide probably more knobs than you really want, but you can tweak most things. And And you can also, for example, if you want to, you can write some process that actually samples the parameters of the queues and then dynamically changes rates if you don't want to use the sampler plugins, for example. But the idea is essentially it often takes quite a while to get into sort of the tuning of the load regulation parameters, but you will want to put in load regulation from the start, and you can put in fairly conservative values. Say you just put a rate limited queue there and 20 requests per second. If it's a new system, you don't have many users, that's going to be enough. And then you can, you're going to hit the load regulator rather than crashing your system if you happen to have some demand. And then you can turn that up and see where the limit is. Now, when I was so Jesper was talking about more advanced queuing algorithms. I'm basically using fairly simple algorithms, but as I said, you can plug in your own queue callback. So if you want to have a more advanced queue algorithm, then you can do that yourself. Now, when I was testing with Dizzy, one assumption I had made from the beginning was that I wouldn't have to optimize for the case where you don't have overload. Actually, we went there with the AXD301. We tried to minimize the latency when the system was not overloaded. And then after a while, we decided that this is entirely useless because obviously there is excess capacity. So, you know, the calls are going to go through, and it didn't really matter if it took, you know, if we shaved off a millisecond or so on a call that was still well within parameters. But Riak really is quite latency sensitive. So Dizzy was not happy with the amount of latency that jobs added, which was not much. It was like 1 or 2 milliseconds on average. But they wanted to stay within 4 milliseconds for most requests. So then actually for that experiment, I made a sliding window algorithm that would try to calculate the incoming rate. Now there are lots of papers on how to do rate estimation. Practically all of them assume a constant input rate. But in estimating bursty input is quite difficult. So you can have an averaging algorithm. For example, the overload library in OTP has an averaging algorithm. Works very well, but it takes quite a while before it has a reasonably reliable estimate of the input rate. So it's actually going to be very conservative. So I was able to create a sliding window that worked well for Dizzy's tests, but then when I was running them in unit tests, the way I was testing it was I would just spawn 5,000 processes that would hit the load regulator at once, and they would all come into the first window and they would all be approved immediately because the algorithm didn't have time to estimate the input rate. So it was entirely useless for bursts. So then my current experiment it actually uses 3 windows. Basically, it's the short-term burst, and then medium-term burst, and then longer-term average. It's getting a bit messy, I would say, and it's really difficult to decide what your rate limiting decision is going to be. But in that experiment, it actually worked well for the Basho bench test, but it's reasonably simplistic in how it applies load to the system. So then the jobs would sort of, half the requests would be approved using the sliding window, and half of them would be queued, and you couldn't really tell from the figures. It would just go seamlessly between the two, which was nice. But then that was for a simple case. And the problem with overload or with load regulation is the edge cases. So I think that doing simple rate or counter-based regulation works very well if you have sort of an input-driven system, or which takes requests from the network. One thing I've come across many times is that people will want to optimize for peak capacity, so that when everything is great, you want to have as much capacity as you can possibly squeeze out of the system. And then you figure that if you have error situations, you'll try to deal with them without crashing badly or whatever. It may be different in different domains, but in telecoms, we actually had these discussions many times, back and forth. Since you never learn from history, the discussions came back over and over again. And what the old-timers would say is that customers, at least in the telecoms sector, are not interested in what your maximum capacity is. They want to know what your engineered capacity or the predictable capacity is. Because that's what they use when they plan the network. Because they don't want to be able to handle 10,000 requests per second on a good day and then 20 on a bad day. Because that will wreak havoc on the system, and it may well lead to other systems in the network crashing, because suddenly your system cannot take the load it's supposed to, and that load is rerouted onto other systems, and then they die, and then that creates even more excess load on the remaining systems, and then they die. And so what they wanted, what at least those customers, telecom operators, wanted was for you to tell them what capacity you could reliably deliver. And we call that the engineered capacity. And for us, that meant that we had pretty much 100% spare, that we had backup nodes that were just sitting there not doing much at all. And it seemed like a waste of hardware, but we could deliver our capacity even if we had failures in the system. And we were using this type of load regulation, mainly rate-based load regulation, with different queues for priority calls, for example, 911 calls or 112 calls in Europe. Always have to go through. Even if you have 500% overload, you have to be able to service emergency calls. So we found that some of the competing systems, they managed the ITU requirement, which was that you could handle 150% of engineered capacity with 90% throughput. But if they got more than that, say 200%, they would die, which would create chaos in the network. And then the other systems that could also only handle 150% load, they would die too. So we ended up having to throttle outgoing traffic to competing switches, because we knew that we had to sense the response times and make sure that we could absorb the load so that they wouldn't keel over, because the operators didn't like that. But that required us to be able to absorb much, much more load than the ITU requirement. And in fact, at least on the old AXD301 switch that we had, we couldn't actually When we allocated all the load generators we had in the lab to one system, we could get it to the point where it was not servicing any more calls, but it didn't die, and it didn't drop any existing calls. But that was something like, it was more than 1,000, I think it was like 1,500% overload or something, where it got to the point where it was just rejecting everything, but it stood up. So I would say that that is a good okay. I was looking at it, it said 39 minutes remaining, but it says 39 hours remaining. It's really hard to enter the right parameters. Okay. So I was just trying to think, oh, how long am I going to have to talk here? So do you have any questions?
How long are you going to talk here?
Yeah, another 39 hours. You can go out and for drinks, and I'll be talking when you get back. Do you have any jobs-related questions?
So did you try it out with Jesper's safety valve?
No, I haven't. That shouldn't be that hard, I guess.
Would it be interesting?
I'm sure it would. So, I mean, what the queue I have does is that it just basically puts everything in, and then you pull out, and then you can measure maximum length and maximum time. And Mahesh has already told you that that's a stupid way to do it.
Depending on the circumstances, it cannot be the smartest thing.
Yeah. So it can certainly be improved, and it would be fun to try to plug in Jesper's queue there too.
Pluggable queue length management would be really cool.
Queue length, pluggable.
Length management. So have the algorithms that you use to, this is for Roberto actually,
Yeah.
take jobs and modify it so that you can instead of filling stuff in the queue, it tells you what it can and cannot do, and you can modify the algorithms that you use for it to tell you what it can and cannot do.
Okay, that shouldn't be. I think always with those things, the one of the hardest things is to figure out how it should be configured, the user interface, how you parameterize it so that people actually understand how to use it.
No, I didn't say it was easy. I said it would be cool to do.
Yeah. So, like I said, Jobs has quite a few knobs already but we can add some more. Contributions are absolutely welcome. Yes? I have tried it with adaptive, the feedbacks on the amnesia. I've done tests like that, and it does work. I also have a unit test where, with a fake sampler, that just to make sure that it actually works and that the rate is actually changing and things like that. But you know, it's a tuning problem. So. Yes, you can combine them. So you can have multiple regulators on the same queue. So you could have, say, 100 requests per second, but at maximum 5 jobs or something. So it will check all the regulators, and then it will come up with a minimum amount of jobs that it can dispatch, given the you know, each each limitation. So that's the way it works. And the modifiers. So
It's, I believe they're going to announce the user of the year, and there's more stuff going on in the main auditorium. So thank you, Ulf. Appreciate
thank you.
this.
Thank you.